namely if R is C of x naught times n, divided by some ideal, yes, and these xi that planes xi ai, then it's of the form a polynomial divided by product 1 minus t to the ai. Yes, and I'll have quite a lot to say about this polynomial. The thing on top is usually very simple. Okay, so let me do an example of this. Which is I'm not wearing a microphone.
That's a problem.
Okay. So let me repeat this thing for x canonical surface. And I want to assume that q equals 0, so chi is 1 plus pg. Right, then the formula is p k p x kx of n is this thing I wrote down, 1 pg and 1 plus pg plus k squared and choose 2. Yeah. So the power series is 1 plus pgt plus 1 plus pg plus k squared t squared, and then plus 1 plus pg plus 3k squared t cubed, and then t cubed, and then plus, similarly with 6k k squared t to the 4th, and so on. Yes. And so the way to understand this power series is, and this happens very, very often. If somebody gives you a sequence of numbers and asks you what the next sequence in the range is, it's very useful. It's very often useful to write not the numbers but the difference between the numbers. So if I do pg minus 1, if I do minus 1 here and then minus pg here, and then minus 1 plus pg plus 2 plus k squared, and then minus 1 plus pg plus 3k squared. Right? So, you can imagine doing this indefinitely, but this just simplifies things very much. So what I'm doing here is long multiplication by 1 minus t. Right, and what I get is 1 plus pg minus 1 t plus, so the pg comes out here, but the 1 remains, 1 plus k squared t squared. And then here, the 1 plus pg, and from now on, 1 plus pg is going to cancel, and this is a binomial coefficient minus the previous binomial coefficient. Right, so this is 1 plus 2k squared. Sorry, the 1 has gone. This is 2k squared t, and then this will be 3k squared, t cubed, 3k squared t to the 4th, plus, and so on, that'll be 4. Yes? So, one of the rules of life is if you enjoyed doing something, you should do it again. And so if you multiply this by 1 minus t, yes, this will become 1 plus pg minus 2t. And then, so there's a little subtraction going on here, which is going to give, I think, 2 minus pg plus k squared t squared. Right, and then here, when I'm subtracting this 1 here, which was sort of exceptional here, became exceptional here, now that becomes exceptional here, is minus 1 plus k squared t cubed. And then from then on, the 2k squared comes from there, this is k squared t to the 4th, and then k squared t to the 5th, and then k squared t to the n for all n. Yes? And now if I do it again, so the consequence is that this, so the consequence, and you know, do this as a serious calculation, is that p x kx of t is 1 minus t all cubed. And here I've got 1 plus pg minus 3 t plus some term here involving k squared and then minus 2pg plus 4 t squared plus pg minus 3 t cubed plus t to the 4. Yes? So there are several things to notice about this formula. So one is the denominator. The denominator is 1 minus t cubed. What this means is that if I take the ring of x and t and kx, right, I can view it, so if pg is greater than 3 and x1, x2, x3 are particularly good, I can view this as a module over, in degree 1, c of x1, x2, x3. So degree 1. Right? And, you know, it won't always work, but if x1, x2, x3 are pretty good, then this will be a finite module. So the thing that's happening on top is the, in a virtual sense, it won't always happen, but you can understand the general case by thinking of it. If x1 and x2 and x3 form a regular sequence for this ring, then the thing on top there is the finite Hilbert series for the Artinian quotient. What happens if I set x1, x2, x3 equals 0? This just means that this ring is a free module over this subring, right? And, you know, I mean, you can make that rigorous, but I'm just saying this is a way of remembering the formula, right? What else is special about the formula? Well, look at the numerator. The numerator has this symmetry. It's palindromic. It's, you know, reading from front to back is the same as reading from back to front. Yes? Also, if you take a numerator like that, you can substitute t equals 1 in the numerator. Or you can take the sum of all the terms in the numerator. Yes? And what you get is k squared. So numerator evaluated at t equals 1 is the sum of the coefficients. And that's k squared. And that says that the growth of the ring with n is k squared, and then, you know, times this coefficient 1/2. 1/2 is the area of a triangle. It's the denominator in the binomial coefficients, right? So this is saying that the plurigenera here grow like coefficient k squared, and then this is n squared over 2. Right? I'm only talking about asymptotic growth there. Yeah, and so you know, I mean, this. You see this when you've seen this formula. It's you know, it has lots and lots of things there that make it memorable. You can remember this formula easily. Yes, and so let's try it out. For example, PG equals 4, k squared equals 5. Yes, so that makes this one easy. This is just t. K squared is 5. This is 5 minus 6 plus 4. It makes this coefficient also 1. So I get 1 plus t squared plus t cubed plus t to the 4th divided by 1 minus t cubed. Yes? And so, you know, it's probable that most of you know a formula for this, a closed form for this long sum. And so this is the same thing as 1 minus t to the 5th divided by 1 minus t to the 4th. Yes? And, you know, one possible model for this guy is x5 in projective space P3. Right? If I put in 4 guys here, as 4 monomials of degree 1, 4 generators of degree 1 there, that's coefficients in P3, coordinates in P3, and then it's reasonable to expect to get a quintic hypersurface in P3. And this formula immediately suggests this. It certainly doesn't prove it. There's no logic here. It just says, and this is, the thing we're doing here is numerology. So, you know, before science, you have magic. So numerology is part of magic. Right? So if you do PG equals 4, k squared equals 6, right? Then you get the same thing here, just one more coefficient here. Yes? So you get 1 plus t plus t, 2t squared plus t cubed plus t to the 4th. Right? And again, I'm going to take out another, I'm going to multiply this by 1 minus t. Yes, and then we'll get 1 plus, there'll still be a t squared there, so I'm going to multiply it by that, 1 minus t squared. Yes, and the thing we get is divided by 1 minus t to the 4th, 1 minus t squared. Yes, so you know, do this calculation. It only takes a few seconds. The thing you get on top here is 1 minus t cubed minus t to the 4th plus t to the 7th. Yes. So when you see 1 minus t to the 5th, you're supposed to be seeing what happens when you take a ring and you divide by a principal ideal. Yes. What you're supposed to think here is there's a minus 3, minus 4, and plus 7 there. You're supposed to see the Koszul complex of a codimension 2 complete intersection in degree 3 and 4. Right? So if I write x 3, 4 in weighted projective space 1 to the 4th, 1, 1, 1, 1, 1, 2. Yes. So there's a polynomial ring here, x1, x2, you know, that 4 x's and a y. Yes, and in here I'm going to have f3 and g4. This is the same as the calculation I did yesterday with x1 times y and y squared equals cubics and quartics, right? And so if I write here r, x, and kx, right, this has a resolution like this with p naught P1, P2, right, where this is the polynomial ring C, the 4x's and the y, and this is, let's call this one S. This is S of minus 3, direct sum S of minus 4, and this one here is S of minus 7. Right. So this sequence here is the Koszul complex of F3 and G4. It says that the ideal of things that vanish on X is generated by F3 and G4, right? And then it says that the F3 and G4 are as independent as they possibly can be. The only syzygy holding between them is G4 times F3 minus F3 times G4 equals 0. Yes? So that's the Koszul complex of a codimension 2 complete intersection. Yeah? And, you know, this formula doesn't prove anything at all, right? But it certainly suggests this. So, you know, there are other cases. This, you know, there are Horikawa and Enriquez and Horikawa and Catanese and his school have a whole story about these surfaces, right? But at least one family here just comes, you know, comes out straight away by looking at this formula. So, you know, just as a kind of last thing, exercise, PG equals 2, K squared equals 1. And so then you're going to get, you know, let me leave this as an exercise, you know, an exercise to do this calculation. What I'm going to get is 1 minus t squared, 1 minus t squared, 1 minus t to the 5th. 1 minus t to the 10th. Yeah? And so, you know, the calculation I'm doing here, this Hilbert series calculation, contains exactly the same ingredients as all of this counting monomials I was doing earlier. Yes? And so when I was doing the monomial calculation, I told you I'm not going to bother with calculating what happens in degree 3 and 4, and then what happens in degree 6, 7, 8, 9, because I know that it must be correct because of this. Yes? So let me give kind of a slightly more, you know, these are just fun examples. You know, I like playing with things and so on. These are beautiful toys. But, you know, this is a sort of serious proposition. If polynomial ring C x0 up to xn, where these are weight xi equals ai, has Hilbert series one divided by 1 minus t to the, well, let me write product 1 minus t to the ai. Yes? And so, you know, you can apply this where all the AIs are 1, and then you'll just get this formula that everybody knows and loves for the number of forms in degree. And, you know, this is basically the proof of the same as the proof of the binomial theorem that you give to undergraduates. So binomial coefficients arise exactly because they're Hilbert series here. The proof, if you write 1 over 1 minus x, this is 1 plus x squared plus x cubed plus, I think you know the rest, yes? And this is the sum over the polynomial ring k of x of, so it's a sum over x over monomials of the polynomial ring M, right? So here's the polynomial ring in one variable, right? And here is just a list of all the monomials in it. Yes? And so if I do product of 1 minus xi, right, I'm just doing the product of those things, and I'm getting, the only thing I'm writing here by writing this infinite product of infinite power series expansions is every monomial in the ring, each counted once. It's just the sum over those monomials. So now if I set xi equals t to the ai, yes, I'm counting the number of monomials in each degree. Yes? And then, you know, if R has a resolution, P0, P1, well, you know, let's just do the simple case. If R is polynomial ring X divided by F, homogeneous of degree D, then I'm getting 1 minus x to the power of d, 1 minus t to the power of d, divided by the same thing. Yes? And that's just, what I'm doing is I'm taking the polynomial ring, and then in degree d, I'm putting in one relation, which means I have to subtract away, the number of monomials in degree d plus n from the number d minus n from those in degree n. Anyway, this is easy. So similarly, if R has a resolution, a free resolution, right, maybe I have something like this. R comes from P0, comes from P1. Yes, this is the polynomial ring S, and these are generators AI, degree di. Then I'm going to get 1 minus some t to the di plus, and so on. Yeah. And so, you know, I mean, if you know, if you do algebraic geometry, at some point you need to know that a finitely generated module has a free resolution like this, a free graded resolution, and I'm just, you know, this is just the same calculation. So I have to put in 1 t to the di for every polynomial generator, and then I have to put in some term here for all the first syzygies, and then for all subsequent syzygies. So, it, you know, I mean, this, if you know the Hilbert series, of course, it doesn't mean that you know this projective resolution, even the numerics of the resolution, but you know something about it. So it often suggests a solution. Okay. So, you know, there's a general. So, you know, this is a theorem, a baby theorem. So if M is a finitely generated graded module over polynomial ring S, then PMT. So the PM, I mean, this means dimension of M in degree n, t to the n, and now the sum has to be over n in z, right, because the module might have elements in degree -1. So here you normally think of the relations here as being, you know, for example, S minus D1 plus S of minus D2. Right. So, you know, I'm in this formula, when I'm writing down this Koszul resolution, I write S of -3, S of -4 here in order that multiplying by the equation f3 and multiplying by equation of degree 4 here is homogeneous homomorphism of degree 0. Yeah. Anyway, it's just a convention. Then P of is polynomial divided by product 1 minus T to the AI. And you know, this is a sort of almost trivial. This is you know, I mean, combinatorialists or algebraists, commutative algebraists were doing this in the 1950s. Just think about xi. Well, let me take the last one, xn, from m to m. Yes, this is some multiplication by xn. Yes, and so this is this has a kernel. And a co-kernel, right? And the main step in the proof is to observe that the kernel and the co-kernel are both modules over polynomial ring S divided by xn. Yes, and so the kernel and the co-kernel are kernel and the co-kernel are finitely generated graded modules over a ring with one fewer generator. So by induction on the number of generators, we can assume the result is true for these, right? But in every degree, this is taking P n, n into n plus AI, right? So we add up these terms and subtract off these terms, and we get you know, end of proof. Yeah. So this is just a very general statement. So I think everybody knows Hilbert polynomials. So if you want to know what's happening in some degree far enough up, you know, you have to, after you've got to the end of Serre vanishing, when Serre vanishing holds for all your subsequent modules, these give you definite formulas. Now for the, okay, so I'm sorry, I shouldn't have said that. If everything is of degree 1, you get polynomial formulas for all subsequent, these numbers here become polynomials for subsequent n. Anyway, I'm sorry, I shouldn't have said that. It's just confusing. In degree 1, you get these things called Hilbert polynomials, but the Hilbert polynomial is asymptotic, whereas here I'm interested in all the terms, including the beginning one. Okay, so there are two stories to go from here. So one of them is called ice cream. And the other one is about curves, K3s, and farmers. So let me just give a preview of ice cream. So so let's look at X7 in weighted projective space 1, 1, 1, 2, 3. So as I said, this has at this point Py. This is a particular point there. This is orbifold of type 1/2 of 1, 1, 1. And this is a third of 1, 1, 2. And so what is Pn of x? So, you know, this is a hard question. So instead I should be asking what is P of x d of t? What is the Hilbert series? Yes? And so this is just the Hilbert series of R of x and O of 1. So O of 1 is minus kx. Yes? And so this is just the polynomial ring in these variables divided by that. So this is 1 minus t to the 7th divided by 1 minus t squared, 1 minus t squared, 1 minus t cubed. Yes? I'm sorry. Right. So you know, when you've done 10 or 20 of these calculations, you will start writing these denominators: 1, 1, 1, 2, 3. Yeah. So this is just the denominator corresponding to the Hilbert series of the graded ring with these things. Yes. And so, you know, I mean, this is a formula. Take this thing, either by hand or in computer algebra, write this out as a formal power series, and you'll get everything that you ever want to know about this ring. Yes? So that's not the question. The question is, can we write this in a form that looks like Riemann-Roch for threefolds or Riemann-Roch for surfaces? Yes, and so this is what ice cream does. So the answer is, so orbifolds, so plus conditions. I'll try and say this a little bit more precisely tomorrow when I start seriously talking about Q-Farnos. Yes, so are going to look like P I of t plus P orbifold of 1 over R of ABC, and then K x. Yes, and so here I've got these 2 points here, and here I've got this kx, in this case is minus 1, right? Kx is Ox of minus 1. So let me just say what the answer is in this case, because it will tell you how to think about the answer in all cases. Yes? So I do, you know, mumbo jumbo, this is magic. Yes? I've got, I'm going to say G equals 1. Right? So a Fano threefold, and also a Q-Fano threefold, has genus defined by H naught. H naught of minus Kx is G plus 2. Right? So here I have 1, 2, 3, and so genus is 1. And so what I write down is 1 plus G minus 2 T plus g minus 2 t squared plus t cubed divided by 1 minus t to the 4th. This is pi. Yes? So the thing that is I about it, the thing that's initial about it, is that this determines the first plurigenus, right? So this is 1 plus g plus 2 t plus higher terms. Yeah? So this does nothing at all except that it fixes this term. So, you all know that 1 minus t to the 4th, 1 over 1 minus t to the 4th is a power series that starts 1 plus 4t. Yeah? When I multiply that inverse with this, I get 1 plus g2 plus some higher order terms. Yeah? So in our case, this is 1 minus t squared plus t cubed. Yeah? So, the way to remember this formula, again, if you sum the coefficients on top, you get 2g minus 2. Yes? And so that is what, the genus of a non-singular Fano is the genus of its curved section. Yes? And so what are these orbifold terms? So P orb of 1 over r, A, B, C. So let me, I might as well assume it's minus 1. Right? This is of the form polynomial divided by product of, divided by 1 minus t cubed 1 minus t to the r. Yes, and the polynomial has also some magic properties that I will explain next time. Yes, and so I don't know if you can see this. 1 minus t to the r. Yes, so if I was doing this calculation that you can still see on the board, then this is, if I have a function that is a sort of step function with period r, then it just removes that periodicity, right? So this is 1 plus t to the r plus t to the 2r, yes? And this allows me to put into the formula, so if I write down how many elements there are here in O of 6, yes, then I'm talking about a Cartier divisor on this ambient space. Yes, by the time I get to O of 6, I've got y cubed and z squared, and so I have a linear system that moves across, away from these singularities. Yes? However, because I've got these singularities, we expect, whatever formula for the plurigenus there is, we expect it to have some kind of periodicity in 3 and some periodicity in 2. And that's exactly what these orbifold terms are providing. Right, so in this case, P of 1/2 of 1, 1, 1 minus 1 is t squared over 1 minus t cubed 1 minus t squared. So, if you just had this t squared over 1 minus t squared, the thing you're looking at there is 1 plus t squared plus t, 1 plus t squared plus t to the 4th plus t to the 6th and so on. it's telling you you get ice cream on evenly numbered days. Yes? It tells you something different happens on evenly numbered days. So, you know, you get one more functional, one more ice cream on each evenly numbered day. Yes? And the P orb of 1/3 of 1, 1, 2 minus 1 is t squared plus t cubed divided by 1 minus t cubed, 1 minus t cubed. Yeah. So the narrative here is that every 3 days you get ice cream on the second day and ice cream on the third day, and then no ice cream on days that are 1 modulo 3. Yes? So, you know, I told you, you need some kind of experience at reading this formula. So I told you, first thing, calculate the dimension of this space. Yes? And then calculate the canonical class of this guy. Right, something else you can calculate is the degree, the order of growth of the plurigenera. Yes? And so the order of growth right, so there's something like 1/6, which is just the volume of a cube in volume of a simplex in 3 dimensions. Right? It's just the denominator in n choose 3. Right? So let's forget about that, but then there's 7 divided by 6. 7 divided by 2 times 3. Right? So in other words, the natural degree of this thing, you have to think of, because this is of degree 2 and this is of degree 3, this y here only produces monomials in even degrees. Right? So it only produces 1/2 of the number of monomials. If I were to add y, square root of y to this business, then I get twice as many monomials. So this, again, 3 times. Yes? So the degree of this is 7 2/3. Right? So what is the asymptotic growth of this? The asymptotic growth of this is, I want this to grow like t cubed, right, is 0. So I take some of the coefficients on top. Yeah, I get 2g minus 2g is 1, so I get 0. Yes? On the other hand, this one here grows like 1/2, right? You know, ice cream every other day. You get half an ice cream every day. And this one grows like 2/3. Yes? And anyway, I mean, this is the magic. This is the numerology. And there's one other magic property that this has, which is this is Bernstein symmetric of degree -1. Yes? So what does that mean? It means if I do P of, if I compare P of t and P of 1/t, right, I get here a sign which is plus or minus 1, and then a power of t, right, and now we have to think which the plus or minus 1 is. Yes, so let's just look at this. If I write 1/t squared divided by 1 minus 1/t cubed 1 minus 1/t squared. Yeah, if I want to write this out again in terms of t, so I have to multiply the bottom by t to the 5th, and then by -1, and I have to multiply the top by t to the 4th, right? So I do t to the 4th times the top, and t to the 5th times the bottom minus, yes? And this is t squared, because I've t to the fourth times 1 over t squared is that. And then here, I'm putting 3 factors of t in here, and the minus sign, I'm getting 1 minus t cubed, 1 minus t squared. Yes? So that tells you which way you should put the sign is minus, and the power of t is it's either there, it's either, I think it's probably, maybe it's right. Maybe it's minus 1. Anybody following what I'm doing? This is P of t, right? This is what I've done with P of 1 over t, and then times minus 1 over t. Yes? Right. And the same thing, exactly the same calculation holds here. Yes? The minus 1 is this. This thing here is palindromic of degree 3, and the base is palindromic of degree 4. And so this is 3 minus 4 is minus 1. And this here, you know, if you learn to read this, this one is palindromic of degree 4, palindromic of degree 4, not 2, 4. Right, this is 0 plus 0 t to the fourth. And when I reverse them, I get, it's symmetric. Yes, this is 4 and this is 5. So this one is 5 and this one is 6. Yes? So I'm just telling you how to do the magic, but this will be... in general, this polynomial is to do with... let me give a formal statement and proof of it tomorrow. Let me make one remark here, which is that you know, it's part of the training of any algebraic geometry graduate student to read a course or a paper on Hirzebruch-Riemann-Roch and Grothendieck-Riemann-Roch. So Riemann-Roch says that chi, so you know, I'm talking about Hirzebruch-Riemann-Roch, but you'll probably read it in the form of Grothendieck-Riemann-Roch. Chi of f on a projective variety is ch of f times tud of x. Yes, so you know, this is 1 minus g plus degree d, or it's this chi of ox plus n choose 2 plus 1/2 d k minus d minus k for a surface, and then for a threefold it's something slightly more complicated, not much more complicated. However, when you get to a fourfold, it is some immensely complicated formula. So the tud 4 is 1 over 720, and there's 5 terms on top. And the terms include things like c2 squared and c1 times c3 that nobody will ever understand. Yes? So, you know, there's a problem here in that there's denominators. Yes? And there are also problems in that these topological terms, Chern characters, Chern classes, Chern numbers, that are really very, very complicated. Whereas this is working here with integers, right? There are fractions appearing here, but they're appearing in these denominators only, right? And so this is orbifold Riemann-Roch. It's Riemann-Roch, including the fact that our sheaves are not always integral, but it doesn't involve any, you know, the coefficients going into ch and the coefficients going into tud have all come out in the wash because I'm looking at Hilbert series. So Hilbert series make the Chern character and Todd classes, they go away or they appear only implicitly. And they also, everything is integral. So, you know, I mean, maybe you think of, you know, the word character here is like characters of finite groups and so on. It's something that comes from algebra, and you know, you've got, if I've got a variety and I'm asking what is the dimension of a vector space, you know, I'm hoping, like anything, that at the end I get an integer, right? And this, the Riemann-Roch formula, this formula involves all kinds of terms. If you're in, you know, 4 or 5 or 6 dimensions, hundreds of terms that you don't understand, and they're all fractional. And so, you know, working with Hilbert series is always much easier. I'm not saying easier is more virtuous. I'm just saying, in a practical sense, we're doing calculations where we expect to be able to understand the answer. It's better. Okay, so let me just say a few words about genuine Farnows. So, canonical curves, K3s, and Farnow threefolds. So from tomorrow I want to talk about Q Farnow threefolds, so I want to talk about things like this guy a little bit more seriously, right? But Farnow threefolds, so you know, Farnow wrote papers from around 1890 to around 1930, and he was concerned with a variety in projective space. So let me write G+1 with the property that if I do hyperplane section intersect V, then I get S in PG, and if I do H1, H2 intersect S, I get C in PG-1, and this is supposed to be a canonical curve. So, you know, this is the phi Kc from C to PG-1, canonical embedding. Yes, of a non-hyperelliptic curve. Yes, conversely, if I have a surface in projective space whose hyperplane section is a canonical curve, it follows, this implies that S is a K3 surface. Yes, so it has Ks equals 0 and H, what else do I want? H1 equals 0. Yes, so the S is in minus Ks. So, you know, I mean, you prove this. For example, it's proved in my Park City lecture notes, but of course it was well known a long time before then. As far as Farnow was concerned, this was the definition. Yes, so, you know, 30 or 40 years after Farnow, Iskowski, possibly others, but especially Iskowski, defined V is Farnow to mean non-singular plus minus KV ample. Yes. So, you know, Iskowski was a friend of mine from late 1970s. We would sort of walk around and he'd say, oh yes, I'm assuming non-singular because we don't yet know how to deal with the singularities. So, we will, now there's a well-defined, a well-established category of singular threefolds called the Murray category, and we can work with Q Farnows. But let me stick with this for the moment. So, yes, okay. So I better not stop too long because somebody wants to use the room. Yes. So the Hilbert series of this V is the thing I wrote over there, right? 1 plus G minus 2 T plus G minus 2 T squared plus T cubed divided by 1 minus T to the 4th. Yes? So this tells you that in degree 1 I have that many, I have G plus 2 sections. Yes? And it, this palindromic property is to do with the canonical class. Right? You notice there's degree 3 here and degree 4 here, so this should be minus the canonical class. Yes? And then, the K3 is just the same thing, but with divided by 1 minus T cubed, and the canonical curve, of course, divided by 1 minus T squared. Yes. So I've given several examples of nice, friendly calculations with algebraic surfaces, but you notice there were sort of 5 or 6 such nice, friendly calculations. So at most about 20 families of K3s that you can handle by really explicit, concrete calculations using graded rings. So for Farnow threefolds, it's known that these embedded guys work for genus. So 2 is sort of a little bit special, but it's there anyway. 3, 4, up to 10, and 12 only. Right, under assuming die prima specie, assuming that pick of V is Z times the anticanonical. Right, so these exist, and you get nice varieties here. I'll maybe explain what happens here for 7 or 8 or 9. So this was Iskovsky in the around 1980, and then Mukai and Murray worked a lot more on this, and then we invented the Murray category of singular varieties. Right, so so the point is that this is a very limited game. You just get a small number of problems here. And so, whereas when I do Q Farnows, we expect to get, tens of thousands of Farnows. And if you do Calabi-Yau manifolds, then as you probably know, there is an existing population of about 500 million, that's 500 million known examples of Calabi-Yau threefolds. So the surface, the non-singular surfaces, the canonically polarized surfaces I was talking about, and these Farnows are sort of quite limited in the number of graduate students you can train, whereas, there are 60,000 numerically possible Q Farnows, of which we know maybe a few hundred. But the few hundred we know give rise to very, very interesting problems, and that's what I want to talk about for the next 2 lectures.
classification of these gate?
You know, what there is a numerical classification. Yes. So you know, based on this, so the numerical type is its Hilbert series. Its Hilbert series is given, as I said here, by a single genus, which, you know, in principle takes integer values, but when integers bigger than 100, you just don't happen, right? You're going to be able to exclude them for some reason. And then this basket of singularities, right? So I'm going to put in, I should have put in summation here. Yes, so there's the basket of singularities is the thing that gives rise to these tens of thousands. Yes, so there's something called, so these are, you know, if you have 60,000 examples of something, it's better not to handle them by hand, right? So, you know, even a very, very well-trained graduate student will get working through a list of only 70 or 80 of these things can make a little mistake, a little slip-up. You know, Iskovsky made a little mistake in this 12, and Murray and Mukai made a little mistake in their little, slightly longer list. So this is a database. This is a computer database, so it's searchable. If you want to know, can you find, you know, a 13th of 167 as a singularity on a Fano threefold, then you can ask the computer. Right? And it will give you a numerical type. And so, you know, there's something like 60,000 numerical types, of which we can really handle completely confidently around 500, right? And, you know, but that leaves problems for the next generation. So, you know, I can give problems, you know, I mean, not just, you know, bulk problems, but really interesting problems in whether these things exist and what properties they have. So, you know, this is an industry. So there are several people at Warwick and several people in other British universities who are still mining away at these Fano threefolds.
Is it Bernstein symmetry some reflection of some duality?
Of course, it's their duality, or it's Bernstein duality. So, you know, I don't want to sort of go into this because it involves a lot of cohomology and so on, but you know, when I'm doing this R of x d, right, then we know when this is Cohen-Macaulay. Yes, and that's if and only if, you know, h I of x d nd is 0 for all I and n except I equals 0 d n positive and I equals n and I equals dimension x and n less than some canonical number. Yes, so we know that the ring is Cohen-Macaulay, and then the ring is Gorenstein is the condition that kx is n is some kx times d with kx an integer. Right, the best case is k equals 0. Right, that's the K3 case. Yes, and so if I take the full section ring here, so I take the whole of all of the sections, the thing that's projectively normal, whatever it's called, integrally closed, then I get a Gorenstein ring, right? And the Gorenstein ring has, you know, Gorenstein is all kinds of different symmetry. You know, if you want to do injective resolutions, it's one kind of symmetry, and so on. But for me, I do this, R comes from P0, comes from P1, Pn, So this is C. And then Cohen-Macaulay is the statement that this C is the codimension. And Bernstein is the statement that this sequence, this series is self-dual. In other words, if I do hom of this into this, I get, So this is, say, a duality at the level of cohomology groups, but it's also this duality of the projective resolution, Bernstein duality at the level of homological algebra. So on the where it comes from is, you can say Serre duality or Bernstein duality, right? However, it is very, very useful because it tells us, this is a short polynomial. Yes, this is wherein the initial term there, the initial term is handling 1 and the coefficient of 1 here. I don't know anything about the higher order terms. And this thing here starts with 2. Yeah? And so I know how to concentrate this into the range exactly because this is Bernstein symmetric. So, that's one of these, applications of highbrow, theory, including, Grothendieck duality and stuff like that, to my, magical numerology. So at least in England, there's a lot of propaganda going on against plastic. So you shouldn't, if you throw it in the river, it'll be killing baby fish and turtles and so on, albatrosses. So please look after the plastic.